go. Okay, so for this one, okay, again, the directions I know I gave weren't complete, but like on an exam or quiz or something, you'll have better directions. So again, what we have is we have that f of x, as you can see, and we have 5/2. So the first thing I did was I show that 5/2 is a root of it, of f. In other words, f of that, I plugged it in and we do get 0. Now again, by the factor theorem, that tells us, by the remainder theorem, that tells us the remainder, if we divide by x minus 5/2, we have to get 0. In other words, x minus 5/2 is a factor of f of x. All right, so let's actually divide now. So we know that x minus 5/2 is a factor of this. That's what this showed. Again, that's by the factor theorem. And the remainder theorem, because f of 5/2 is the remainder, and we get 0. So 5/2, that's here. Again, it's f, the dividend, is in standard form. Okay, there's no missing powers of x, as you can see, between the leading term and the last term, which is the constant term. So we list the coefficients: 2, 13, minus 5, minus 100. We have 5/2 here. Okay, so the first 2 comes down. 5/2 times 2. If you do that, the 2's cancel, and you get 5. 13 plus 5, 18. So we do the same thing again. 5/2 times 18. 5/2 times 18, right? It turns out if you do that, you get 45. Mostly because the 2 cancels with the 18, and the 18 becomes 9, and 5 times 9 is 45. Minus 5 plus 45, right? That's 40. 5/2 times 40. If you were to do that, you would end up with 100. So minus 100 plus 100, that's 0. The quotient is degree 2, because this is degree 3. Okay, we have that. Okay, so we have the quotient is 2x squared plus 18x plus 40. Again, the quotient is degree 2. It's 1 less than the degree of the dividend. The remainder is 0, as you can see. The remainder is 0. And again, we saw that already from this slide, right? That's what this is. So altogether, the remainder, the last term is 0. So we get f of x is this, x minus 5/2 times the quotient. Normally you would add in the remainder. The remainder is 0. All right, cool. Let's keep going. We can factor this. I mean, we actually could have factored the original by grouping, but now we have another way of doing it, mostly because we know we have something that is a factor of it. Okay. Okay, so from here, Well, can we factor this? Well, it looks like we want to use the AC method. However, and you can see from here, 2 is a factor of itself, 18 and 40. And there is a non-zero constant term here. What's nice, though, is, okay, so because of that, excuse me, the GCF of this would be just 2. So there's a non-zero constant term. You can't factor out x. 2 is a factor of itself, 18 and 40. So 2 you could factor out. That's what I'm doing here. And so we get 2 times x squared, right? You divide everything by 2 to get what's left over, plus 9x plus 20. This is a lot easier to deal with, right? We have a trinomial of degree 2. Leading coefficient is 1. So because of that, right, we want 2 numbers whose product is 20 and whose sum is 9. Well, you can see what the numbers are already from here. 2 numbers whose product is 20 and whose sum is 9, 4 and 5. So we have this. Okay, that's great. So now that we factored this, we're actually in a sense done. What I did here was I put for the quotient, I put this in, and then I used the fact that this is equal to this. So altogether, we get this as our factorization. Although what you could do as I did is you can take the 2 and distribute it. You can take the 2 and distribute it among the first one here, as we're doing. Mostly because you want your polynomials to have integer coefficients and integer terms. Excuse me, integer coefficients and constant terms. That's why. I mean, if you did leave it like this, for me, that would be fine. But if I really wanted to be precise, I would do this step here. Mostly because, again, we want the terms, as you can see here, to have coefficients that are integers and constants that are integers, because we're working with polynomials whose terms are integers. So, but again, if you stop here, that'd be fine. I might be saying a little more than I should. All right. I hope that made sense. Are there any questions about that? I figured I start chapter 5 now. Oh, well, yeah, I guess I could start it. 5 minutes left, but that's okay. Let me close this then. I gotta stop that and I'll get the chapter 5 notes. As I said before, chapter 5, okay, that is trigonometry. And again, I'm not going to do everything. The book actually goes into the kind of trigonometry you're going to see if you take pre-calculus. So I'm not going to cover everything there. What I'm going to cover is in section 5.1, which is angles and which is radians. That's a unit of measurement for angles. That's used a lot when you get the calculus. What I'm also going to cover is SOHCAHTOA, which is the next section. Let's keep going. So in this section, as I just said, what we want to do is first look at angles. I mean, to really understand trig, you really need to know a bit about angles. And 1 unit of measurement you have seen, I hope, if you haven't, that's okay, I guess, is degrees. That's used a lot more in society around us, degrees. Like turn 20 degrees to the right, or turn 50 degrees to the left, something like that. You might see that more around us today in society. Another unit of measurement that mathematicians use, which turns out to be mathematically nicer, is radians. That's another unit of measurement for angles. Why it's nicer, well, that takes a little bit of work to explain, so I'm not going to do that for time consideration. But let me just introduce to you what an angle is, well, like as a reminder. I mean, if you really want to define what an angle is, right, you need to know first what a ray is. I have the definition here. You could think of a ray as, I mean, I don't want to say half of a line, because that's not really precise, because a line doesn't have a finite length. You know, the length of a line is infinite. What you can do is take a point on that line, okay, and everything on the line on one side of the point, you throw away. So you're looking at that point and everything on the line on one side of that point. So if you imagine doing that to this line, it's going in both directions. You know, you take this point, let's say, where that little laser cursor thing is, everything on the left, we disregard. Everything on the right, that's on the line, we keep. Okay? And we get a ray. You know, I know it's tempting to say, oh, well, it's half a line. Well, it's not right to say that, because again, a line is infinite in length. Now, infinity is not a number. This point, though, is called an endpoint, as you can see. And essentially down here, I mean, we'll get to this next time, but using this ray, if you rotate about its endpoint, you end up forming an angle. Basically, this is the after picture, I guess, when you're forming an angle. You know, basically, you rotate it about that endpoint. This is the starting position of the angle. This is the angle's initial side. This is its terminal side. All right, we have less than 10 seconds. So let me stop